Today, our speaker is Kateryna Kustareva with the talk Asymptotic Properties of Compact Sets in Flows Generated by Equation with Interaction. Please, Kateryna. Kateryna,
You're muted.
yeah.
Okay, thank you so much for the introduction. Can you see my screen and hear me?
Yes. Now
Okay,
okay.
I'd like to begin with a definition that is already, I guess, familiar to most of the audience, but I briefly want to recall it. So SD with interaction. Such kind of equations were proposed by Professor Drogovtsev in 2003, and general form of such equation is following. As you see here, x, ut represent the trajectory of a single particle that starts at point u in the RD, and next mu t is a probability measure that describes the mass distribution of the entire system at a given time t. And the WdPdt represents a Wiener sheet over RD times the interval 0 infinity, and is a model of the random media. And I'd like to consider this stochastic equation in the context of data evolution. So here, suppose each initial point u can be viewed as an individual data sample, for example, a single observation or feature vector. And the stochastic flow phi then describes how this data point evolves in time under both randomness and interaction. And in the interpretation, the flow phi acts as a transformation of the data manifold. So it captures how uncertainly mutual influence between samples. And I can see regularization mechanism change the overall data distribution mu. So rather than studying one isolated trajectory, we analyze the collective dynamics of the entire data set. And this perspective is very close to how modern machine learning models treat data. For example, in diffusion models or stochastic gradient dynamics, where the entire population of samples evolves stochastically toward a more regularized configuration. The main idea is the same. So since we can interpret the stochastic flow as a transformation of the data manifold, let us now look at it from a geometric point of view. Instead of focusing on individual trajectories, we can treat the whole collection of initial point as a compact set K0 from RD. And as the system evolves in time, this compact moves under the flow X and producing a family of images, KT. So this formulation allows us to analyze how the shape and structure of the set change over time. To analyze the evolution of the compact set more precisely, we introduce a lifting into a separable Gilbert space H. So suppose we have a map H, act as a feature embedding, similar to how we lift nonlinear data in machine learning using kernel methods. So we define the lifted compact set as AT. And this transformation allow us to study the evolution of K in a linear and analytically convenient space. And the geometry of A encodes both the internal structure of K and how it changes under the stochastic flows. In machine learning, this corresponds to embedding data into a reproducing kernel Gilbert space. And again, where nonlinear relation between samples become linear in the feature space. And the diagram illustrates the idea of kernel embedding as a nonlinear lifting. At the bottom, we have the original compact set K0 and KT inner D, suppose. They represent the data in its initial and evolved forms. And through the embedding map, our H, we lift this set into the Gilbert space H. And in this higher dimensional space, the geometry becomes linear and easier to analyze. So suppose distance, angles, projections in H corresponds to similarities and relationships in the original nonlinear data. And this is exactly what happens in kernel methods. We just embedding data into a reproducing kernel Gilbert space. So, and then we can describe complex nonlinear patterns using simple linear tools. Next, I want to show several real-world examples of kernel embeddings. For example, in medical diagnostics, sensor data such as heart rate, temperature, blood pressure can be embedded using a Gaussian kernel. By the way, it was first introduced by Vapnik. And this kernel captures smooth psychological dependencies and nonlinear correlation between patients. And it allows us to model variations and similarities that cannot be described by simple linear metrics. The second example is image recognition. We often use polynomial or radial basis function kernels, for instance, and this type of kernels help to linearize complex image structures, such as shapes and textures, so that in the feature space, similarities corresponds to this geometric proximity. And this is a foundation behind methods like support vector machine and kernel PCA. And the third one, speech recognition. And you can see the Laplacian kernel is often applied because it's more robust to shape transitions and noise in the signals. And it captures some similarity even when data includes strong fluctuation, which makes it particularly effective for some base speech features. So across different domains, medicine, computer vision, and so on, the same principle holds. A kernel embedding transforms nonlinear structure into linear Gilbert space representation. And then we can analyze. Now what we have seen how data can be lifted, we can move from visualization to some quantitative analysis. And in this lifted space H, every compact set A has its own geometric complexity. It's a way to measure how rich or irregular structure is. And to study the evolution of such complexity, we introduce several entropy type functionals. Quadratic entropy, Kolmogorov entropy, Talagrand's functional, effective dimension, and Gaussian width. Each of these captures different aspects. And our goal is to analyze how these quantities behave for the evolving compact AT. Okay, each of these functionals originates from different area. Quadratic entropy was introduced by Andrei Anatольevich Drogovtsev to measure the geometric complexity of random compacts in stochastic flow, and it acts as an analogy of total free path time in one-dimensional stochastic flows, describing the orthogonal structure of evolving set. And this idea was proposed in work Drogovtsev and Popov. Next one is Kolmogorov entropy. Kolmogorov entropy dates back to the works of Kolmogorov and Tikhomirov in the 1915s. It measures how many small epsilon balls are needed to cover the set. So essentially a geometric form of information content. Then the Talagrand functional, introduced in 1996, and describe regularity conditions for stochastic processes. Effective dimensional, directly connected to machine learning. It quantifies how many degrees of random of freedom are effectively active in a kernel. Or it can be a Gaussian process models too. So it serves as a spectral measure of information concentration. Finally, Gaussian width. So measures the stochastic spread of convex or compact sets, and key in empirical process theory and concentration inequalities. Lots of work, Sudakov, Ferenik, Talagrand. We will see some of them. Okay, now let us look more closely at the first of these quantities, quadratic entropy, introduced by Drogovtsev in 2010. So for a non-empty set A, subset of a Gilbert space H, the quadratic entropy is defined as follows. As you can see here, H2A equals supremum some norm PUN squared, where PUN denotes the orthogonal projection of the element UN onto the orthogonal complement of the span of all other elements. So UK such that K not equals N. And let us look at two examples. First one, orthogonal system. A equals 0 together with the elements AN, EN, where EN is an orthonormal system in a Gilbert space. And for the discrete orthogonal set, the quadratic entropy is simply the sum of squared of the coefficients. So H2A equals the sum over N of N squared. The second one, we consider a linear subspace of finite dimension D, and assume that all elements of A inside the subspace have norms not exceeding R. Then the quadratic entropy is bounded by D times R squared. And if this set actually contains the orthogonal vectors of length r, we reach equality. Our entropy equals d multiplied r squared. So this simple example shows that quadratic entropy reflects both dimensional and scale. It increases when the space expands in more orthogonal directions or when the amplitude grows. The second one is Kolmogorov entropy, introduced in 1958. So for a compact set A in a Gilbert space H with epsilon greater than 0, the Kolmogorov epsilon entropy is defined as follows. Epsilon H epsilon A, which is equal log of n A epsilon, where n A epsilon is the smallest number of epsilon balls needed to cover the set A. So in other words, we imagine covering the entire compact A by closed balls of radius epsilon. Let's look at some examples of Kolmogorov entropy. And first, consider a d-dimensional ball. A equals b sub e of 0 and the radius r, and where the dimension of e is d. In this case, we can estimate the covering number. So n a epsilon is roughly proportional to r over epsilon to the power d. And then taking a logarithm, we get that our entropy behaves like a d times log of r over epsilon. And this result comes directly from comparing the total volume of the d-dimensional ball of radius r and with the volume of a single epsilon ball. So that's how we get the minimal number of coverings. And the second one, it's indicator curve in L2. Let A be the set of indicator functions on 0t and for t in 0, 1. And here the distance between two such functions equals the square root of t minus s. And we keep this distance below epsilon. The difference between t and s must be less than epsilon squared. So roughly, we need a mesh of step epsilon squared to cover the interval 0, 1. And from this, we get that the covering number n epsilon n a epsilon behaves like epsilon to the power minus 2, and consequently, our entropy behaves like log of 1 over epsilon. The next one is effective dimension. And now let us move again to the compact subset of the Gilbert space H. And let mu be a probability measure defined on A. And here we define the second moment operator of mu as the expected tensor product of a random element eta distributed according to mu. So formally, as mu equals the expectation over eta of eta tensor eta. So since this set A is bounded, this operator is trace class, which means it has a discrete sequence of eigenvalues denoted lambda I. And now we normalize this spectrum by dividing each eigenvalue by the total trace. So we have rho I equals lambda I divided by the sum of all lambda. We then define the quantity d mu A equals x of the negative sum over I of rho I ln rho I. And finally, we call it effective dimension of A. So it's just obtained by taking the supremum of d mu A over all probability measure mu supported on A. So this value tells us how many independent component or degrees of freedom the component A really occupies. And in machine learning, the same quantity appears in a Gaussian process like regression. And where it quantifies how many eigenmodes of the covariance operator contribute significantly to the model. And I want to show the example how we can calculate this effective dimension on an ellipsoid. So we take a d-dimensional subspace E spanned by the orthonormal basis vectors EI through ED. So, and consider the ellipsoid A where AI greater than 0, and the length of it's the length of semi-axis. So, and then the point AI EI are the endpoints of the axis of the ellipsoid, and they are used to construct the probability measure. So since each axis has 2 endpoints, there are exactly 2D such points in total. And then we introduce a discrete probability measure concentrated on these 2D points, mu star, and where the normalization constant C is determined from the total probability condition. So we have this condition, and then we can easily take in this one. From this, we obtain this constant, and this means that each axis receives a weight proportion to 1 divided by a j squared. The shorter the axis, the larger the weight assigned to it by the measure. So what is S mu? The next questions is the expected tensor tensor product of the points of the set weighted by the probability measure mu star. And in simpler terms, S mu is analog of a covariance matrix, but defined in a Gilbert space. And it captures how the mass of the measure is distributed along different directions. And then we can substitute our points plus minus AI, EI into the expectation, and then we will have this result. Because the plus minus sign disappears when we multiply. So, and this means each pair of symmetric points contributes equally to the operator. And now we can substitute everything, together into our expectation formula. And since both probability I equals are given by 1 divided by 2 constant 1 divided by AI squared, we obtain our S mu star. And as a result, since the normalized spectrum is uniform, so we can calculate the MUR and equals T. This means that the spectrum is uniform. It means that all directions contribute equally to the total, can we call it energy of the set. So the effective dimension of the ellipsoid is like geometric dimension. even though the ellipsoid must have different axis lengths, but the property normalized measure makes all directions contribute equally. So as a result, in a uniform and fully d-dimensional structure, we can see the result of T. Okay, the next one is gamma 2 functional, which was introduced by Michel Taralgran to describe the multi-scale geometric structure of metric spaces and to connect it with the behavior of Gaussian process. So now let's see how it's constructed. So we start with some metric space, TD. And for instance, you can think of T as a compact subspace of a Gilbert space. And the idea is to approximate T step by step using a sequence of partitions. So we denote P0, P1, P2, and so on, each one given a finer and finer description of the set. And at the very first level, P0 contains only one cell, and this is the whole space. Then at level n, the partition Pn splits this space into at most 2 to the power 2n cells. So the number of parts can grow exponentially with n. So each new partition P refines the previous one, adding more details at a smaller scale. So for any subset...
But I think this growth seems like super exponential or something, because we have 2 to the n.
I agree.
Mm-hmm.
So yes. Each new partition refines the previous one. Again, for any subset B inside T, we define a diameter, which is the supremum of the distance between points in B. And that tells us how big the cell. So now fix a point T. At each scale n, the point T belongs to a unique cell, which we call BNT. And the diameter of this cell, we calculate like a supremum distance, supremum D between S and T. So it measures how well T is localized at scale n, how precisely we know its position after n refinements. And then we combine all these scales into a single functional, gamma. Gamma 2 equals the infimum over all admissible partitions P of the supremum over all points T of the sum over n of 2 to the n over 2 times the diameter of BNT. Intuitively, this weight sum reflects a hierarchical approximation. At small n, we capture global structure, and as n increases, we measure finer local details. If the set T is well structured, there exists a good sequence of partition that keeps all diameters small. So our gamma 2 will be small. But if T has complicated geometry, for example, many thin branches, then no matter how we partition it, the sum of these weighted diameters will remain large. And I want to say all the functionals we have discussed related to the continuity property of a centered isonormal process on the compact set under consideration, and we will see and how we can use it and list some of the well-known estimates. And the first one is the theorem generic chain bound, which was proposed by Talleyrand, and let xt be a centered Gaussian process with a canonical metric. And then there exists universal constant, CNC capital, greater than 0 such that this inequality holds. So this means that the gamma 2 functional provides an exact characterization of the expected supremum of any Gaussian process, not just an upper or lower bound, but two sides equivalence. And the sequence T represents like successive reinforcements of the space T. And at each scale, we approximate every point T by a representative Tn, and like pay a penalty proportional to their distance, weighted by 2 in power n over 2. So, and this construction called generic chain, so it captures like the structure of the index set and all scales simultaneously. So, and this eliminates the gap between Sudakov's lower bound, Dudley's upper bound, which we will see now. So, and the exact asymptotic order of the like Gaussian supremum. So the next well-known result, theorem from Sudakov. Assume we have a Gaussian process xt, and suppose that in our metric space there exist m distinct points t, such that all of them are well separated. And the distance between any 2 points, Tp and Tq, at least a positive number a. Then Sudakov's lemma tells us that there exists a universal constant L, such that roughly proportional to the square root of the logarithm of their count. So lemma establish a lower bound. It's like separation in geometry always for high stochastic complexity. Okay, the next one is Dudley's theorem. We can consider centered Gaussian process xt indexed by a metric space T with canonical metric, and Dudley provides that there exists a universal constant L greater than 0, such that expectation supremum of xt less or equal L multiplied by the sum 2n over 2 ENT, where ENT denotes the minimal radius of a covering of T by at most 2 in power 2 and metric poles. So this means that the expected maximum of the Gaussian process is controlled by how effectively we can cover the index at T using small metric balls at different scales. And passing to the continuous limit, this discrete inequality becomes the well-known Dudley's entropy integral, which you can see, and where anti-epsilon is the minimal number of epsilon balls needed to cover T. Dudley's theorem connected like the geometry of the index set with the probabilistic behavior of the Gaussian process. It gives a universal upper bound. And later, Talleyrand will refine this result into two sides equivalence using the gamma 2 functional. Okay, now I will show how it's possible to connect three types of estimates that we discussed before. The gamma 2 functional Gaussian supremum and the quadratic entropy introduced by Andrei Anatolyevich Dorokovtsev. So let A be the set of all elements A, N, En, where N is greater or equal than 1, and where the sequence En forms an orthonormal system in the Gilbert space H, and the coefficients A and are assumed to be non-increasing and they converge to zero. Then there exist universal constants C and C capital greater than zero, such that for independent standard Gaussian random variable xi, variables xi(n), we have the following bounds. So C times the supremum over m of am times square root of log m is less than or equal to our gamma of a, and gamma of a is less than or equal to C times the same supremum. So equivalently, C times the supremum of am times square root of log m is less than or equal to the expected value of the supremum of an xi(n), and that in turn is less than or equal to C capital times the same expression. And moreover, the sequence an belongs to L2, then if the series of n of an squared is summable, then the quadratic entropy of A is given by this formula as we see before. So, and therefore gamma 2 of A is less than or equal to C times the square root of H2 of A. So, and results show that all three quantities are connected and to describe the same order of complexity. So let us prove, and let's start with covering number. And the first step is to compute the covering number for our orthogonal set A, and we fix some level epsilon greater than 0, and look how many epsilon balls are required to cover the set A. So formally, we define NA epsilon. That means we take all indices n for which an is larger than epsilon and add one more ball to include the origin. So indeed, if two different coefficients AI and AJ is larger than epsilon, and add one or one more ball to both let these coefficients IA and AJ both greater than epsilon, then the distance between these corresponding points satisfy inequality, so such points cannot be covered by the same epsilon ball. So they required distant ones. So meanwhile, all the smaller coefficients contained within a single epsilon ball around the origin. Okay, the next step, we move to upper bound for the expected supremum of the Gaussian series. We start from Dudley's integral inequality, which provides general estimate for Gaussian supremum. And here, an A epsilon is the covering number that we already computed on the previous slide. So next we denote m epsilon, and this function counts how many coefficients are larger than a given epsilon, and it says and it stays constant on each interval am plus 1 am. And using that, we can rewrite the integral as a sum. And now, because the sequence am is decreasing and the function square root logarithm 1 plus m is increasing, we can apply a partial summation argument. So, and this yields to the estimate. Therefore, we can conclude that expectation of the supremum an xi n less or equal constant multiply supremum am or multiply a square root logarithm n. So, and this gives us desired upper bound. Now we establish the lower bound, and here we can use Sudakov minoration theorem and show how it perfectly aligns with the gamma 2 functional. So we start with some simple geometric observation for any integer m. The first m points are pairwise am separated. And this means that no two of these points lie too close. They're all well separated by at least am. And now by Sudakov's minoration theorem, this separation immediately give us the lower bound. And if now we take the supremum over all m, we obtain this result.
And what do we mean by this interesting inequality sign?
Again, sorry.
What do we mean by this curly inequality sign? Yes, this one.
Yeah,
The
because
second.
it's like a probabilistic lower bound.
Mm-hmm.
Okay. Next, this gives us the matching lower bound to the one we derived from Dudley integral earlier. So we can link this with the gamma 2 functional. We use the majorizing measure theorem, which we already seen by Talleyrand. And combining this inequality, we get the final equivalence. So it closes the chain of arguments and show that the orthogonal system, all three for orthogonal system, all three approach leads to equivalent estimates. Okay. Then we move further. So let am again. We have finite truncations, and for orthogonal vectors, Drgov's quadratic entropy satisfies the exact identity, which we already seen. And by monotonicity, and since am goes to A, under increasing unions of compact sets, we can get this result. So for orthogonal system, the quadratic entropy is exactly the L2 energy of coefficients. So, and combine it with the previous slide, we can take this result. And now we have introduced both functional stellogram gamma 2 and Drgov's quadratic, and we can compare it. So we began with the one-side dimensional result. If the sequence AN is non-increasing and belongs to L2, then we have well-known estimates, and this means that the growth of the Gaussian complexity term AM squared log m is controlled by the total quadratic energy of the coefficients. And to justify this inequality, we note that since this sequence is not increasing, so hence we get this result. And because the term of supremum is finite, the bound follows. So we can combine the estimate with the previous lemma, and we obtain the chain of inequalities. And the this provides a clean upper comparison between the Lagrange and the Rogovtsev measure of complexity. And however, the reverse inequality generally falls. It's possible to have a sequence AN for each sum of AN squared equals infinity, but the supremum is less than infinity. So, and the square of the Rogovtsev entropy equals infinity, while gamma remains finite. And similar estimates make it possible to conclude that the following theorem holds, which provides a necessary and sufficient condition for the existence of a continuous modification. So let A be a compact subset of a separable Gilbert space H, and let eta U belongs to A, be the isonormal Gaussian process, satisfying that expectation eta U, eta V equals scalar product U and V. And if eta, it means a continuous modification on A, if and only if there exists an orthonormal basis in H and the sequence epsilon k belongs to L2 such that A contained in a Gilbert-Schmidt brick. So this is a great and well-known result from Drogovtsev and Popov. So let's back to the SDs with interaction. I just want to recall it and let phi denote the stochastic flow generated by this equation. And we start from a compact initial set K0 belongs to RD, and we define it like KT equals phi t of K0 as its image, the image of the compact set under Anderson flow. And to study the geometry of the evolving compacts, we apply a bounded linear operation H from RD to H into a separable Gilbert space and define AT equals H of KT and A0 H of K0. So then we fix a closed ball B containing K0 such that the flow maps it into another bounded ball almost surely. And this ensures that the derivative of phi is bounded on the region, and we can define the LT star like local Lipschitz bound for the flow, which is supremum norm DFTZ. So, and I want to present the main theorem. Under the assumption we discussed above, for every t greater equal than 0 and every epsilon, we have two inequalities. The first one is Kolmogorov entropy, and the second one is the Rogovtsev entropy. The first one, it tells us that the covering number of set A, the number of epsilon balls needed to cover it, cannot grow faster than the Lipschitz constant L of the flow. And in other words, if the flow expands distance, but by at most L. And then the complexity of the image set AT increases by at most the same factor. And the second inequality concerns the quadratic entropy, and it expresses exactly the same type of contraction property, but measures in L2 sense. So it controls the average geometric spread of the set under the flow. Okay. Now let's prove. And to prove it, we fix a closed ball in RD that contains the initial compact set K0. And since the stochastic flow phi is continuously differentiable on this ball almost surely, we can take any 2 points x and y in our K0 and define the line segment in the interval 0, 1. And by the theorem of calculus, we can rewrite like a difference of the integral, and then take a norm on both sides. We give this part. And since the derivative is bounded on the ball, we can replace the integral by the supremum of the derivative of the ball. So, and hence the flow phi is locally Lipschitz on K0 with the constant LT star. And therefore, for all x, y belongs to K0, we have such an equality. So then I explain the proof of the first part of the theorem, the bound of the Kolmogorov entropy under our flow. So if mapping T is Lipschitz, it means that the distance between points can increase by at most an L. So formally for any set A, which is subset of H, the covering number satisfies this inequality. In other words, if we want to cover the image TA by balls of radius epsilon, it's enough to cover the origin set A but the balls that every epsilon over L times smaller. And now we apply this to the specific map THF, where F is a stochastic flow and H is a bounded linear operator mapping into Gilbert space. So, and then the total Lipschitz constant of this composition satisfy the inequality. And using this property of covering numbers, we get an inequality for the Kolmogorov entropy. Okay. To prove the second part, we need some additional lemma, Lipschitz contraction of the gamma 2 functional. So let K0 be a compact subset of RD, and let phi t from RD to RD be denote the stochastic flow generated our interacting our SD with interaction. And we also take bounded linear operator H, mapping into a separable Gilbert space, and assume that the norm of H equals 1 for normalization. And we then define AT again, and A0. And the flow phi acts on the initial compact set, and the operator H embeds its image into the Gilbert space. So, and allowing us to measure its complexity there, we can define our LT star, which is the primum of the norm derivative phi t of that, and then the gamma 2 functional satisfy this inequality. Its result means that the stochastic flow is Lipschitz with respect to multiscale complexity. So in other words, the flow cannot increase by gamma 2 complexity of a compact set by more than Lipschitz constant L, and it preserves the structure of the set across all scales. So let's prove this result. So let T be the composition of H2 phi, and by construction, T is Lipschitz. Satisfy the Lipschitz property and the closed ball B that contains K0. And then we take any admissible sequence of partition Pn with P0 equal 1 and then 2 in power 2n. And Pn plus 1 defines Pn. So, and then we define the push forward partition of AT by this rule. And because T is satisfy the Lipschitz property on B, it doesn't merge or break the refinement structure. So T P0 equal 1, TP and 2. So, and hence TP is also admissible. So for any cell B then, and for any X and Y belongs to B, the Lipschitz property gives us this result. And taking supremum over X and Y yields the diameter estimates. So where the supremum holds. Okay, let's continue. And for any U belongs to AT with pre-image U belongs to A0 such that U equals TU, the multi-scale sum defining gamma 2 functional, satisfying this inequality. And taking the infimum over all admissible sequences P and the supremum over U, we obtain our result. And hence, we can say that gamma to AT less or equal L square gamma of A0. So this proves the Lipschitz contraction property for gamma 2 functional. So, and then we can back to our second result. And finally, we combine this with the equivalence between quadratic entropy and the gamma 2 functional. Again, we have the map, L, the Lipschitz constant on K0, and then applying the previous lemma, we get this result, which completes our proof. Hence, the quadratic entropy growth at most quadratically with the local Lipschitz constant of the flow, which is complete the proof. So then here's my references from Telegram, Ledoux, Vereshcheny, Dudley, Vapnik, and some optimization. And thank you for your attention.
Okay, thank you very much. And it was interesting talk. Maybe somebody have questions or comments, please.
Excuse me. Could you please go to page 16?
Okay.
I have a small question about the construction.
Okay, 16, yeah. Okay.
Okay. Actually, I didn't understand how the multi-scale partition works. Therefore, I also don't understand the inequality here. I mean, how you partition the P0, P1, and P2.
So again, use a sequence of partition, which is P0, P1, and so on. Each one given a finer and finer description of the set. So, and at very first level, we mentioned that P0 contains only one cell, the whole space. Then we split the space into at most 2 to the power 2n cells for the all levels. So the number of parts grows. And each new partition refines to the previous one.
I see. So the inequality exactly comes from your construction. And that's all equal to 2 power 2 power n.
Mm-hmm.
I see. Thanks.
Yes, and we define, yes, diameter, which is the supremum, the distance between points in our subset B inside.
Okay, thank you very much. Maybe somebody else have questions or comments, please.
And what exactly breaks if we take the number of elements in Pn to be bigger than this number? Do we have some like divergent sequence in this case?
Again, we want to put the number of points more than the number of cells. This is the
Yeah,
idea.
I mean, what if the size of Pn grows faster?
Okay, maybe I will answer. Vadim, you see here in the last line the sum and the sum 2n over 2. What is this? This is square root of logarithm, yeah, of the previous quantity. It means you still have more or less the same estimation like for Gaussian variables. You have to remember that if we have independent Gaussian variables standard, then to bound the sequence, we have to divide them onto square root of logarithm of n. Then when we discuss the boundedness of Gaussian process on the initial space T, we also need this square root of logarithm. Of course, we have no now independency, but we have some inequalities like Slepian inequality, Sudakov estimation, and then we can do more or less the same. So if we have some estimation on Pn, we must have the square root inside of the sum of the logarithm. Of course, you can try, and I think that it will work. Take not 2, but 3, for example. And also take logarithm and square root.
Interesting, thank you.
You're welcome. Okay, maybe some other questions, please. Kateryna, am I right that you discuss only the cases when all these characteristics of complexity of the compact, of lifted compact, remains to be finite? So you did not discuss a case, for example, when quadratic entropy blows up at some moment t.
Yes, it's always, yeah, it's always,
Yeah,
always.
because you use this Lipschitz condition, but
Yes.
just imagine that you have such situation that the derivative blows up somewhere at finite time horizon. Then one can expect that maybe complexity of the lifted compact also can blow up. You see? Let's think about this. Let's think. Nevertheless, thank you very much for interesting talk with a lot of information. And as far as I understand, next week we have a conference. Am I right, Georgi?
No, next Tuesday we have a talk
Oh, I see.
by Maria Belozerova.
Okay. Okay, Maria. Then we will wait for your talk. And then I understand that we have to correct schedule of the conference. Okay, we will do this. Thank you very much, Kateryna. And for today, that's all. Thanks, everybody, and see you next week. Bye.
Thank you. Bye.
Thank you for interesting talk. Goodbye.
Thank you, bye.